Hello and welcome to this video lesson on ionic bonding. It has spec reference 3.1.3.1 and 3.1.3.4. First of all, as usual, let's have a look at our learning objectives for this video lesson. And the first one is that we want to know that ions form when electrons are transferred from one atom to another. That's how we form ions. Secondly, we want to know how to predict the charge of a simple ion based on the group of the periodic table that it's in. Next, we'll have a look at compound ions. You might know those as molecular ions. We need to know that they are made up of groups of two or more atoms that have a charge. Then we're going to have a look at the formulas of various compound ions. And we're going to memorize those. Fifth, we're going to have to know that the electrostatic attraction that holds ions together is called ionic bonding. And then we're going to work out the formulas of ionic compounds, given that they are neutral. And we'll also know that ions form crystals. And those crystals are made up of giant ionic lattices. Then we're going to specifically look at the structure of sodium chloride, and that'll be it for this lesson. So you remember from GCSE that ions are formed when electrons are transferred. Okay, I'm going to underline transferred because that's the key word in this statement. The electrons are transferred from one atom to another, and they're of course transferred from the metal atom to the non-metal atom. But let's just concentrate on the loss first. So let's have a look at a sodium atom and see how that forms an ion. Now from your periodic table you'll see that sodium has an atomic number of 11, and so its atomic structure, so sodium, its electronic structure is going to be 2, 8, 1. 2 electrons in the first shell, 8 in the second, 1 in the third. And so we can draw that atom if we just let the nucleus be the symbol like that. And then the first shell we'll put like that. We need 3 shells. So we'll write the shells like that. Quickly switch colour to draw the electrons. So in the first shell we're going to have 2 electrons, maximum 2 in the first shell, and then in the second shell we're going to have 8 electrons, and we're going to pair them up. 2, 4, 6 and 8, and of course we've got that last lonely electron. Let's draw it there in the outer shell. So that's a sodium atom, and when it forms an ion, it's going to get rid of that outer electron. It's not very tightly attracted to the nucleus. So that's the first shell, that's the second shell, that's the third shell, and of course the electrons in the 2 inner shells are unaffected. But in the third shell, there is no electron. And so because the electron is negative and the ion has lost that little bit of negative stuff, then what remains is positive, because of course in the nucleus there is still 11 protons. So 11 plus for proton. And there is still 11 protons in the nucleus of the ion, and so there is only 10 electrons, and so this has now a overall charge of +1, 1 plus, and that's how we draw it. We draw it in square brackets. So the symbol of this ion would be Na, and the electronic structure would just be 2, 8. sorry, the symbol would be Na plus, and the electronic structure, of course, would be 2, 8. And the equation, if we were doing an equation for that, we would have the Na sodium atom, and that's gone to an Na plus sodium ion because it's lost an electron. That's how we would write the equation there. So that was a metal atom losing an electron, transferring an electron. Now we're going to have a look at a non-metal, and why don't we pick chlorine. So chlorine has an atomic number of 17. So let's just write it up there to remind ourselves. So that means when we draw a chlorine atom, it's going to have an electronic configuration of 2, 8, 7. And there's going to be two, let's draw the shells. Right, first shell, second shell, third shell. And let's draw in the electrons again, 2 in the first shell, and then 8 in the second shell, and then 7 in the third shell. And just 1 there, so it's 1 short. So I'm just going to change colour and then draw a little empty box there to show that chlorine, of course, is 1 short of a full outer shell. Because just like sodium got rid of its outer electron to leave its second shell full, and therefore that would be a stable electronic structure. Chlorine, being a non-metal and with a nearly full outer shell, needs to gain 1 electron to make that 7 up to 8 and therefore be full and stable outer shell. So that's a chlorine atom, and when that chlorine atom forms an ion, it's actually going to gain an electron. All right, so the chlorine, let's draw our shells. There's our inner shell, there's our second shell, there's our third shell, and we still have our 2 in the first shell, we still have our 8 in the second shell, and we have our original 7 in the third shell, but it would gain 1. Let me put that in blue. All right, it will gain 1. That's what it wants to do, because when it does that, it gets 8 electrons in its outer shell, and therefore that's very stable. That's what it wants. But now it's an ion, we have to put it in square brackets. All right, and we had 17 plus charge in the nucleus, 17 protons, but now we've got 18 electrons, so that's 1 extra electron. That electron is negative, so we have a net 1 minus charge on the ion. And if we wanted to draw the equation for that reaction there, we had the chlorine atom, which turned into a chlorine 1 minus ion after it gained that electron. So these two examples that we've done are quite simple, with just the transfer of 1 electron, transfer away in the case of sodium, transfer to the ion in case of chlorine. But of course that's not always the case. So for example with magnesium, when we have a magnesium atom and that forms a magnesium ion, it actually gets rid of 2 outer electrons, and so that's how we would write that equation. And a non-metal that's not in group 7 would be oxygen, and when that oxygen atom makes an ion, it gains 2 electrons to become an oxygen 2 minus ion, like that. A couple of other examples. So now what we're going to do is we're going to just move on to remind ourselves about how we work out the charge on an ion using the periodic table. And we'll probably remember that it's the group number that gives you the charge on the ion, because the group number gives you the number of electrons in the outer shell. So here's a periodic table, simplified periodic table, and let's first have a look at group 1 elements. So group 1 elements, of course, have 1 electron in their outer shell, and so they are going to lose 1 electron. Lose 1 E minus, and they're going to make a 1 plus ion. Whereas in group 2, they're going to lose they're going to lose 2 electrons to make 2 plus ions. Then let's go over to the non-metal side. Now in the non-metals, of course, the non-metals have nearly full outer shells, and so they want to fill them up. So in group 6, those elements need to gain 2 electrons to make a full outer shell. So 6 plus 2 equals 8. So if they're gaining 2 electrons, so they're going to gain 2 electrons, and they're going to make 2 minus ions. And then group 7, in a similar way, they have 7 electrons in their outer shell. They want to get 8 electrons in their outer shell, and so they're going to need to gain an extra 1. 7 plus 1 equals 8. So group 7, they're going to gain 1 electron, and they're going to make 1 minus ions. I just want to clarify aluminium for you, because aluminium's worth noting. When you study the periodic table, you'll remember that we drew a little staircase that's round about here to differentiate the metals from the non-metals, and it's a little bit ambiguous because the metallic property decreases around that staircase, but aluminium is definitely a metal, and that's in group 3. And so in just the same way as the other elements, group 3 means it's got 3 outer electrons, and it's going to lose those 3 electrons, and it's going to make a 3 plus ion. So aluminium, when it makes an ion, is an aluminium 3 plus ion. So that's how you work out the charge on an ion, by finding it in the periodic table and looking at what group it's in. However, it's not quite as simple as that sometimes, because sometimes we get molecular ions or compound ions, and that's what we'll have a look at next. So these compound ions or molecular ions, they are ions that are made up of groups of atoms that have an overall charge. So the group of atoms will have gained or lost electrons, or in fact protons sometimes, and that will give them a charge which makes them an ion. So let's have a look at a list of the compound ions that you'll want to be familiar with. So here's our list. We've got ammonium, carbonate, hydroxide, nitrate and sulfate. And the formulas of these you do well to remember, so I'm going to write them down, and then you can memorize them in your own time. So ammonium is NH4+, and the ammonium ion comes from an ammonia molecule that's gained a proton, usually from an acid. And if I just draw it for you, you'll see a certain point. So ammonia, as you will probably remember from GCSE, is NH3, so a nitrogen atom bonded covalently to 3 hydrogen atoms, and then when it reacts with an acid, it gains a proton, and that proton is also known as a hydrogen ion, and that proton gives the ammonium molecular ion, a +1 charge, and so that's what an ammonium ion looks like. And carbonate, you'll probably remember from studying calcium carbonate, which was CaCO3. All right, so the CO3 is the carbonate ion, and that has a 2- charge, because you'll remember that the formula for calcium carbonate is CaCO3, and now you know that calcium is a 2+ ion, and the whole thing has got to be neutral, so that means that the carbonate must be a 2- ion to cancel out those 2 pluses. Okay, hydroxide, from the study of alkalis, OH-, and nitrate, as in nitric acid, and many other substances, NO3, and it's a 1- ion. And sulfate, as in sulfuric acid, for example, is SO4, and that's a 2- ion. So you'd do well to remember the charge and the formula of those compound ions. So now we're going to remind ourselves about ionic compounds, and here we say that the overall charge in an ionic compound is neutral. But first, let's just unpick this statement. Ionic compound, you'll remember, is made when a metal, for example sodium, reacts with a non-metal, for example chlorine, to make sodium chloride. So that's the ionic compound, sodium chloride. And what we're saying is the charge on the whole compound is neutral, even if the sodium ion is a 1+ ion, and the chloride ion is a 1- ion. So you see the 1+ and the 1- cancel each other out, so the whole thing is neutral. And we can use that to work out the formulas of ionic compounds, knowing the charges on the ions. So why don't we do the reaction that happens between sodium and chlorine. So sodium, you remember from earlier on, is atomic number 11, so it's got 281 electronic structure, so that's got 3 shells with 2 electrons in its first shell, 8 electrons in its second shell, and 1 lonely electron in its outer shell. And when that gets the opportunity to react with a chlorine atom, so our chlorine atom has a periodic, has an atomic number of 17, and so the electronic structure is going to be 287, which adds up to 3 shells as well. And the first 2 shells, of course, are all full. But in chlorine's case, it's got 7 electrons in its outer shell, just like that. And so then when it reacts, when they react together, this, let's go to light blue, this electron here is transferred to this little slot here. And so our sodium atom becomes a sodium ion. It's still got the first 2 shells are just the same, that are still full, but it's now got no electrons in its third shell, so I won't even bother drawing an empty shell. I'll just put the square brackets in there, like that. And it's lost an electron, so it's a 1+ ion. And the chloride ion now has gained that electron, that little blue electron. So our chlorine first 2 shells are just the same, all full up with, although I'm drawing these electrons as green, of course they're identical to the sodium electrons, electrons and electron. But I just want to highlight the fact that there's 1 extra electron. Right, so it's still got its 7 original electrons. 2, 4, 6 and 1 is 7, and then we will draw in the electron that it got from the sodium, and then put the square brackets in and give that its minus charge. So you can see that's the reaction, and as far as the equation is concerned, then we had a sodium atom, we had a chlorine atom, and we made sodium chloride like that. And the point about that is that because we want to make a neutral compound, and because the sodium is 1 plus and the chloride is 1 minus, we know that the formula is going to be a 1-to-1 ratio, which is why we write it simply as NaCl. Okay, let's do a slightly different, slightly more complicated example. Let's do magnesium chloride. I'm choosing that one because it's not a 1-to-1 relationship, and you'll see that a little bit clearer. So let's do magnesium. All right, so magnesium, you can see from the periodic table, has an atomic number of 12, so its electronic structure is going to be 2s2, which means it's going to have 3 shells. A bit wonky, sorry. Let's draw in the electrons. Okay, so we're going to have 2 full shells. And it's going to have 2 electrons. Let's draw them here. 2 electrons in its outer shell because it's in group 2. Let's draw a couple of chlorine atoms. So just like above, we're going to have 3 shells. 1, 2, 3. And let's fill those in. 1, 2 in the first shell, 8 of course in the second shell, and 7, 2, 4, 6, 7 in the outer shell. And so it wants 8, so one of these electrons here is going to go here to make our chloride ion rather. But of course magnesium still wants to lose another electron. This electron here is now on its own, and magnesium wants to lose that still. But the chloride ion has its full outer shell, and so it can't take any more. It's not going to take an extra electron into its 4th shell. That's not going to happen in a month of Sundays. So what we do is we need to use another chlorine atom. Alright, so we'll draw another similar one with 3 shells. And fill them all up. And our 7 electrons in that chlorine atom, and so this electron here is going to move into that space there. And for the sake of completeness, let's just draw that out. So we're going to have our magnesium ion now. So it's lost its 2 outer electrons, so it's only got 2 shells left. So we'll draw the first shell and the second shell. Right, and as is the case with ions, all the shells are full. So let's just fill them up. 2 in the first, 8 in the second. But the magnesium ion still has the same number of protons in its outer shell, and it's lost 2 negative electrons, so what remains must be 2 plus. And that's going to run out of space here a little bit, and so because we have to draw 2 chloride ions. So our chloride ions has to have the 3 shells. The 3 shells are full now, whereas in the atoms, of course, they were less full, not full. So 1 shell, 2 shell, 3 shells, and if you just let me save time by not filling in the first 2 shells, I will now just fill in the outer shell like that. It has its original 7 plus the one that it got from the magnesium atom. Alright, it's got a charge on it, so we have to put it in square brackets and give it a 1- charge because it's got 1 extra electron, and we have to draw exactly the same thing again. So that's going to be 3 shells. I'll just squish them up so I can fit them in. Right, again I won't draw the electrons on the inner 2 shells, and we will just complete our 3rd shell, which was the original 7 plus the second one that the magnesium lost, and that also has a 1- charge. Okay, so that's how we would draw the ionic compound. And as far as the formula is concerned, you can see that we have between magnesium and chlorine, you can see the ratio is 1 magnesium ion to 2 chloride ions, and so that's how we write the formula. We write Mg1Cl2, but of course we don't bother writing ones in the formula, so we just say MgCl2. That's how we get the formula from the charges on the ions. Okay, magnesium chloride is fairly easy. So let's look at another example just to make sure you get the concept. Let's say you were asked to write down the formula for sodium nitrate. Sodium nitrate. And so you would start off by saying, well, of course, sodium makes a 1+ ion, and nitrate, we learned a couple of slides ago, nitrate, the formula for a nitrate ion is NO3-, and so we've got a 1+ ion and a 1- ion, so our ratio to make it the compound neutral need only be 1:1, and therefore our formula of the compound, we use that information, our formula of our compound would be NO3, sodium nitrate. And lastly, let's work out the formula for calcium chloride. So what's the formula for calcium chloride? So calcium is the metal, and you see from the periodic table that's in group 2, and so that's got 2 outer electrons that it wants to lose to leave the previous shell full, and so when it does that it would form a calcium 2+ ion, whereas chlorine is in group 7, has 7 outer electrons, and needs 1 there to make it up to 8, and a full stable electronic structure. So if it did that, it would make a chloride ion with a 1- charge. Alright, so now a 1:1 ratio wouldn't do in this case, because that would still leave the compound as 1+. So the ratio that you would need in this case would be, if you had 1 of these, you would need 2 of those. So 2 1- cancels out 1 2+. Right, so the formula that you would get would be CaCl2. Actually, why don't we do one more? Let's do quite a tricky one. Let's do aluminium oxide. Okay, so what's the formula of aluminium oxide? Okay, aluminium, metal, group 3, 3 electrons in the outer shell, so it forms a 3+ ion, so Al3+. Oxygen, non-metal, group 6, 6 electrons in the outer shell, and so therefore would make a 2- ion. Okay, so how do we make this neutral? Well, 2 and 3 are common multiples of 6, and to make 6 pluses we would need 2 aluminium ions, and to make 6 minuses we would need 3 oxygen ions. Alright, so 2 times 3 plus is 6 plus, and 3 times 2 minus is 6 minus, so the whole thing would be neutral. So that would be the ratio of our ions in the compound, which leaves the formula Al2O3. Okay, moving on to the next idea we want to remind ourselves of, really, is that ionic compounds form a structure when they're in crystalline form. They form a structure called a giant lattice. So let's just make sure we understand these words. So lattice, that just means it's like a regular structure, regular being, repeating. It's a regular repeating structure. And giant means that the basic unit, repeats over and over again. So if the basic unit, say in sodium chloride, was NaCl, that unit NaCl repeats over and over and over again. And that's possibly explained better using a picture. Right, so we've got a picture here of sodium chloride crystals. If we took one individual crystal, say we took this one here, that would, all of the ions in that sodium chloride crystal would be joined up to each other. So there'd be billions and billions of ions all joined up together in a massive repeating regular structure. And when I say massive, of course, I mean massive in terms of number of ions. There'd be billions of ions, not necessarily massive in terms of scale. And lastly, let's have a look at an atom scale diagram of a sodium chloride lattice and point out some features of it. Say, if you look at this part here, you can see that these unfinished lines would lead to other ions, and that's to illustrate the fact that it goes on and on and on until you reach the edge of the crystal. And what we want to say about these straight lines are the ionic bonds. They're to represent the ionic bonds, and they are, in fact, all bonds are electrostatic attractions. Electrostatic attractions between the positive charge on the sodium ion, and in this case here the negative charge on the chloride ion. So we're going to write the electrostatic attraction between oppositely charged ions. So it makes a shape whereby these sodium ions are next to the chloride ions, and the sodium ions aren't as near, they're further away from the other positively charged sodium ions, and that's the same for chloride ions as well. They're closest to the sodium ions and they're furthest away from the other chloride ions. But you can see that it's not like a molecule. The formula might be NaCl, but what NaCl tells you in the case of ionic compounds is just the ratio of the ions in the giant lattice. So lastly, now we're going to have a look at physical properties. Physical properties such as melting point, such as conductivity, and such as solubility. And what we can say is that those physical properties of ionic compounds are determined by the structure. All right, so the structure being this giant lattice. The giant lattice of charged ions, of charged particles. Right, so the fact that we've got a giant lattice of charged particles, that's what determines the melting point, the conductivity and the solubility of these compounds, these ionic compounds. So one by one, let's have a look at them. First of all, here we've got solubility, and on the left hand side you can see we've got an ionic compound, this white crystalline stuff in the bottom of the beaker, and it's being dissolved in water. And so if we were able to look at it at an atomic level, you would see that here on the left hand side you have the undissolved sodium chloride. So the sodium ions, the positive ones, and the chloride ions, you can see them all there in a regular structure. And then you can see them sort of being attacked by these water molecules. So this for example is a water molecule, and you can see that's polar. So when you've got a water molecule, I'll just explain why it's polar while we're at it. Okay, that's a water molecule with the straight lines being covalent bonds. And of course a covalent bond is the sharing of two electrons, like that. And what happens of course is that the oxygen, being a non-metal that's very electronegative, draws these electrons towards itself. All right. So it gets a greater than fair share of those electrons, which leaves itself as slightly negative and leaves the hydrogens both as slightly positive. And that's illustrated there in the diagram. And so that polar nature of water allows the water molecules to sort of attack the bonds in the lattice and grab the ions. There's a sodium ion that's got some bonding there between the hydrogens of several water molecules, and the same and the opposite is true of the sodium ions. So ionic compounds are soluble in polar liquids. Is the conclusion from that. Okay, moving on, it looks like we've got a diagram here to help us think about melting and conductivity. All right, so here we have solid ionic compound, and you can see there's a regular lattice of positive and negative ions, and those ions can't move in the lattice. And so if they can't move, they can't carry charge. All right, so if they can't move, they can't carry charge, and therefore solid ionic compounds do not conduct electricity. Whereas when you melt them or you dissolve them in water, these ions are now mobile. And if they are mobile, they can carry electrons, and they can pick up electrons. So in this case, with a negative electrode being on the left, all of our positive ions are going in this direction, and our negative ions are going towards the positive electrode. And in that way, they carry and pick up charge, and they complete the circuit, and so they do conduct electricity. So molten, which is just melted, and aqueous, solutions of ionic compounds, they do conduct. Okay, so that is conductivity and solubility. And let's lastly have a look at melting. Okay, so these electrostatic attractions, right, the ones that exist between, let's draw it in red, the ones that exist between the ions of opposite charges, they are strong electrostatic attractions. And if they are strong electrostatic attractions, that means the ionic bond is strong. And if the ionic bond is strong, that means it's going to take a lot of heat to break it. And by definition, what that means is that the melting point is high. Okay, so that's the point about melting points, is because the electrostatic attraction between oppositely charged ions is strong. That means the ionic bond is strong, which requires a lot of heat to break it, and therefore the melting point is very high. And there we have it. And that just leaves us to recap our learning objectives, make sure we've done them all. We learnt that ions form when electrons are transferred, all right, so they are lost by metal atoms and they're gained by non-metal atoms, so we did that. Did we also learn that how to predict the charge of a simple ion based on the group? Yes, group 1, 1 plus, group 2, 2 plus, group 6, 2 minus, etc. We did all that one. Thirdly, compound ions. We looked at a few compound ions. We saw that they were groups of 2 or more atoms that had a charge. Right, so I'm just going to write plus charge in there, because they're not ions, of course, unless they have a charge. And we mentioned that. We also looked at the formulas of those compound ions. We looked at sulfate, SO4, 2 minus, hydroxide, OH minus, nitrate, NO3 minus, carbonate, CO3, 2 minus, and ammonium, NH4 plus. Yeah, so we went through all of those. And then we mentioned that electrostatic attraction between oppositely charged ions, that's what holds the ions together. That is the ionic bond. So there we can tick that one. And we worked out a few formulas of ionic compounds, given the fact that ionic compounds are neutral. Crystals. Yes, we saw a picture of a crystal and we saw an atomic level diagram of sodium chloride, so we can tick that and that. Okay, hope that's been clear, and if not, let me know.